Good morning. I am DHANALAKSHMI, Associate Professor in the Department of Computer Science and Engineering. I am going to deliver a lecture on CPU scheduling, which is one of the important topic of operating systems. Nowadays, everywhere, everyone is using computer. So before moving to CPU scheduling, we should know what is operating system. Without operating system, we can't do any task by using the computer. So operating system is acting as an interface between user and hardware of the computer. So this is the structure of the operating system. This is the structure of a computer. In this structure, computer hardware is available in the lowest level and the user processes are available in the topmost level. So all the user processes are executed by using the operating system only. So here, for all the user processes, the resources are allocated, are given from the hardware. So that the hardware, from the hardware, operating system is allocating resources. User processes cannot directly get the resources. So here, operating system is acting as an interface between user and hardware. In general, that the hardware is having some set of devices like central processing unit, which is used to execute the program, and then a memory which is used to store the applications or programs, and then input output devices which is used for performing I/O operations. So here every user processes can execute their program only by using the resources. So that can be given by the operating system. So here operating system is called resource allocator. It is also used to control and coordinate all the operations of the computer. And here that operating system is providing an environment in which user can execute their applications. One of the important feature of operating system is multi-programming. So that is, one user can execute multiple applications at a time. So usually all the applications are available or stored in primary storage device called disk or hard disk. If we want to execute or open an application, that application should be loaded into the physical memory or primary storage memory. It is also called main memory, and then that program can be executed. So the processes or the files available in the secondary storage device cannot be executed directly from there itself. So it has to be loaded into the physical memory and it can be executed. So once that processes are available in the secondary storage device, they are called files or programs. So once it is going to be stored or going to be loaded into the physical memory, they are referred as process. So all the files available in the secondary storage device can be loaded into the physical memory and they are referred as process. Every process is having three important data structures. They are program counter, stack and data section. So program counter is used to hold the address of the next instruction to be executed. Then stack is used to store all the temporary results of the process during its execution. Then data section is having the important information about the process and the data required to execute that particular process. So a process is nothing but program in execution. Then information about the process is stored in a block called program control block. It is also called PCB. So for every process there will be a unique PCB. So a process control block is created. So the process control block, it is maintaining the information about the process like process state, then program counter value, then what are all the CPU registers are used by that particular process, then in which memory location that the process is loaded, and what are all the set of processes or files opened by this particular process, then what type of I/O operation that process is going to perform or already it has done. So all these informations are maintained in process control block of a particular process. So during a process execution, that process may available in different states. So there are 5 states for a process: new, running, waiting, ready and terminated. So new means once a process is created, that process is loaded into the physical memory. So at that time that process is in new state. Then after, so now that process has collected all the resources and it is waiting to get the CPU. Without using CPU or central processing unit, the process cannot continue its execution or even start its execution. So it needs CPU. It needs CPU. So a process has collected all the resources, but it is waiting to get the CPU. So in that time, that process is called ready state. That process is in ready state. And after getting the CPU, that process can start its execution. So that state is called running state. Then after some time, that process may want to perform IO, input output operations. So in that time, it may waiting for getting the IO devices. So at that time, that process is waiting for is available in waiting state. So here there is a difference between waiting state and ready state. Waiting state means that the process is waiting for getting IO devices or waiting for performing IO operation, input output operation. But in the case of ready state, the process has collected all the resources, but it is waiting to get the CPU to continue its execution. Then once that process execution is completed, it will go to terminated state. So this is the process state transition diagram. So in this, initially that process, once it is created and loaded into the physical memory, it is in new state. From the new state, after collecting all the resources, that process is waiting for assignment of CPU. So it is in ready state. Then after getting the CPU, that process can start its execution and it will be in running state. And from the running state, that process may either go to waiting state or again will move to ready state. So running state, from the running state, that process, suppose it wants to perform any input output operation, it will go to waiting state. So at that time, that CPU can be assigned to some other process. And after completing its IO operation, that process again will go to ready state. That is, that process is now ready for execution, waiting to get the CPU. Then from the running state, that process may also go to directly ready state. Here, suppose during the process execution, if any new interrupt or system call is arrived, that the process, that CPU can be allocated to service that interrupt. So at that time, that the process cannot proceed its execution. So its execution is suspended and that process may go to ready state. And once that process execution is completed, it will go to terminated state. And during a process execution, that process is migrating between different queues. Operating system is maintaining three important queues. They are job queue, ready queue and device queue. Job queue is containing all the set of processes ready for execution. Once a process is ready for execution, they are not directly loaded into the physical memory. First, they are placed in job queue. Then from the job queue, the set of processes are selected and they will be loaded into the main memory. So all the processes available or residing in main memory are maintained in a queue called ready queue. And then every device in the operating in the computer is having their own queue. They are maintaining their own queue. For example, suppose and a particular process wants to perform IO operation. So in that time, that process may need a particular device. If that device is not available, then that process may be stored or placed in its respective queue. So in this, let us assume, suppose 3 or more documents are printed by using the printer. Suppose your new process is sending the request for printing. So if the printer is not available, then that process cannot be immediately printed. So that process will be stored or placed in its respective printer device queue. So in this way, that processes are migrating between different queues during their execution. Then, as I already told, operating systems are supporting for multi-programming concept. So multiprogramming concept is introduced only to increase the utilization of CPU. So in multiprogramming environment, that is more than one application can be executed by the user at a time. So in this environment, CPU cannot be retained in one particular process. It can be moved between different processes frequently. So moving the process CPU from one process to other process is called context switching. So during that context switching, or before moving that CPU from one process to other process, that CPU has to store all the current information of the currently executing process, and then it will be allocated to or assigned to new process. So in this case, let us take two processes, P0 and P1. So P0 and P1, how that CPU is switching from P0 to P1. So how it is moving between these processes. So initially CPU is assigned to P0 and it is executed here. So it is available in executing state or running state. Suppose a new interrupt is occurred. So once that new interrupt is occurred, CPU is preempted from that currently executing process, and it has to be allocated to service that interrupt. So before allocating that CPU to this service that interrupt, it has to store all the current information of the P0, and then it will be that the CPU will be allocated to the new process. Similarly, P1 is getting that CPU after some time. So this is in this period that the process is in executing state, that is running state. So CPU is allocated to process P1. So before starting that process P1's execution, CPU has to reload all its previous information, and then it can continue the execution of P1. So in this way, CPU is moving between different processes. Why we need CPU scheduler? So we are going to talk about CPU scheduling. So why we need CPU scheduler, or what is CPU scheduling? Operating systems are supporting for multi-programming or multitasking. That is, at a time more than one applications can be executed by the user. So here in this case, but we are having only one processor, that is CPU. So in uniprocessor system, one CPU is there, but more than one applications are ready for execution. So among that multiple applications, one process can be executed by the CPU at a time. So we have to select, that is, that operating system has to select one process for assigning CPU. So in this case, how that process is selected? So in this example, let us consider there are 4 processes ready for execution. They are available in physical memory, residing in physical memory, and in one portion of the physical memory, operating system is residing. Now among that 4 processes, that one CPU should be allocated to one particular process. So among these 4, that process 5 is selected for assigning CPU. So how that process 5 is selected among these 4 processes? So this can be done by the scheduler, and this is called CPU scheduling. So that the scheduler, there are different CPU scheduling algorithms are there. By using that CPU scheduling algorithm, we can select one particular process for assigning CPU. So at what situations that a CPU scheduling decision should be done? So in 4 scenarios that a CPU scheduling decision should be taken. That is, suppose a process is switching from running state to waiting state. That is, that process is executed by the CPU at present, and now it wants to perform some IO operation. At that time, it cannot retain CPU with that particular process, so it will release that process, and that process, that CPU can be allocated to some other process. At that time, CPU scheduling should be taken. That is, to which process that the CPU should be allocated next. Then switches from running to ready state. A process is switching from running state to ready state. So that a process is executing by the CPU, and suppose any high priority process is arrived. At that time, the CPU is preempted from this particular process, and that will be allocated to the next process. Then switches from waiting to ready. Suppose a process may perform input-output operation. After its I/O operation is completed, that process will go to ready state. That is that the process is ready for execution. So waiting to get the CPU. And once that process execution is completed, terminated, that is one process execution is completed, so automatically CPU should be allocated to another new process. So in this four conditions, CPU scheduling decision must be taken. So among these four, so before that, CPU scheduling, there are it is supporting for two types of scheduling. One is non-preemptive and another one is preemptive. Non-preemptive means once CPU or processor is allocated to a particular process, that CPU can be released only by that allocated process. It cannot be preempted by some other process during that particular process execution. But in the case of preemptive, a process is executing by that CPU, but at any time that process can be that CPU can be preempted and can be allocated to the new process. So this is called preemptive scheduling. So here that first condition, first scenario and the last scenario is supporting for non-preemptive. So in both cases, that particular process is voluntarily releasing that CPU. So CPU is not preempted from these two cases. But in the case of the second one and third one, CPU is preempted from currently executing process, and that will be assigned to some other process. So we can perform, that is operating system is performing CPU scheduling by using different CPU scheduling algorithms. So one operating system can implement one particular CPU scheduling algorithm for making that scheduling decisions. So the most commonly used CPU scheduling algorithms are first come first serve scheduling, shortest job first scheduling, priority scheduling, round robin scheduling, and then multi-level queue scheduling, and then last one multi-level feedback queue scheduling. So these scheduling algorithms are deciding at what time which process should be selected for assigning CPU. So the first method, first come first serve scheduling. See, in this case, processes are selected for assigning CPU, the order in which they are arriving into the ready queue. That is the order in which they are sending the request. The first process sending the request to get the CPU is getting the CPU first. So this is very simple to implement. The next method, shortest job first scheduling. Shortest job first scheduling, so in general, all the processes can be associated with their burst time or otherwise CPU running time. So in that case, a process with the minimum burst time is selected first, and that will be allocated to the CPU for execution. So this shortest job first scheduling is supporting for both preemptive and non-preemptive. So non-preemptive means again a process is currently executed by the CPU and a new process is arriving. That arrived new process priority or a burst time is smaller than that currently executing process. Still that CPU cannot be preempted from that particular process. That process can continue its execution, and that process can release that CPU only when its execution or its burst time is completed. But in the case of preemptive, CPU is executing by the CPU is executing a particular process, and suppose a new process is arriving with the smallest burst time. So immediately that the CPU is preempted from that currently executing process, and that will be allocated to the newly entered process. So in general, that is shortest job first scheduling algorithm is producing optimal results. The next scheduling algorithm is priority scheduling. In priority scheduling, with each and every process, their priority is also given. So for every process, priority is assigned. That priority is represented here as an integer number. So a particular process with the smallest integer number is representing highest priority process. So here a process with the highest priority is getting the CPU first. So this is also supporting for preemptive and non-preemptive. Preemptive and non-preemptive scheduling. But here the problem of this particular algorithm is starvation. That is, low priority processes has to wait for longer period of time to get the CPU. So sometimes they never get the CPU. So this starvation problem can be solved by using a technique called aging. That is, this algorithm can periodically check that ready queue and find all the waiting processes, and for all the waiting processes it will increase that priority of that processes by 1. So automatically at one time that waiting processes priority is also increased and they will be getting the CPU. The next one, round robin scheduling. In round robin scheduling, for CPU, some time quantum is given. That is, every process can get the equal chance. Every process will be executed for a particular period of time. And that processes will be taken from the ready queue one by one. That is the order in which they are arriving. Suppose a process is executing by the CPU and that process, its execution is not completed, still it need a particular CPU, means once its time slice is elapsed, immediately that process is preempted from that CPU, and that process will be attached with the end of the or the tail of the ready queue, and the CPU will be assigned to the next process available in the queue. And here the important feature of round robin scheduling is every process can get the CPU in equally, and here the performance of this algorithm is based on the time quantum fixed by the operating system. That time quantum should not be too low or too high. If it is too large, then it will become, this algorithm will become FIFO. If it is too small, then periodically CPU will be moving from one process to other process, and definitely this is a overhead and it will reduce the or degrade the performance of the algorithm as well as performance of the computer. So selecting the time quantum is very important. It should be the moderate value. It should not be too low or too high. The next scheduling algorithm is multi-level queue scheduling. Here in all the 4 algorithms we maintained, that is operating system is maintaining only one queue, that is ready queue. From the ready queue the processes are selected and they will be assigned to the CPU. But here in multi-level queue scheduling, multiple queues are maintained. Multiple queues are maintained and all the processes are directly loaded into its respective queue. That is, based on the nature of the process, that process will be directly loaded into or placed into its respective queue. So here that queues are arranged in the hierarchical order. That is, system level processes are having highest priority than student level processes. So all the system level processes are loaded directly into the topmost queue, and all the student level processes are loaded into the lowest queue. That is, the lowest queue processes are having lowest priority. So here each and every queue can have or queue can follow its own scheduling algorithm, but generally all the topmost queues are following round robin scheduling, and all the lowest queue is following first come first serve algorithm. So in this case, one particular process queue processes can be executed only when its top level queues are empty. So here that student level processes can be executed by using the CPU only when all the remaining top level queues are empty. So here this multi-level queue scheduling algorithm is giving importance to the nature of the processes, and depending on the nature of the process they will be executed first. The next one, multi-level feedback queue scheduling. In multi-level feedback queue scheduling, the processes are moving between the queues. In the previous case, the processes are not moved between the queues. Initially, during that arrival time itself, the processes are placed in their respective queue. But in the case of multi-level feedback queue, all the processes are placed in the topmost queue. Initially they are placed in the topmost queue, then based on their burst time they may be moved to their lower level queues. So here the aim of this particular algorithm is to give preference to short burst time processes. So short burst time processes are executed first, and the processes with the highest burst time are getting the CPU later, and they are executing, their execution is completed after some time. So in this example, let us consider 3 queues are there. All the processes are initially placed in the topmost queue. So here in the topmost queue, that scheduling algorithm used is round robin with a time quantum of 8 millisecond. In the middle level queue, round robin with a time quantum of 16, and that lowest level queue is using first come first service algorithm. So here all the processes are arriving at the topmost queue, and all the processes are taken one by one by the CPU, and that way they will be executed only for 8 milliseconds. If a particular process is not completing within that 8 millisecond time, then it's that particular process is removed from this particular queue and will be moved to its lower level queue. That is, its priority is decreased. And similarly, the processes available in the middle level queue can be executed only when all the top level queues are empty. So here all the processes can be getting the CPU and can be executed only for 16 milliseconds. Suppose still a process execution is not completed, still it need to get the CPU, means that the process is removed from this queue and will be moved to its next level. So in this way, that multi-level feedback queue, that the processes are moving between different queues. So we discussed 6 different CPU scheduling algorithms. But among that CPU scheduling algorithms, we have to select the best algorithm, or we have to find the best algorithm. So the performance of these algorithms are evaluated by using the measures like CPU utilization, throughput, turnaround time, waiting time, and response time. So CPU utilization means a particular algorithm should keep the CPU as busy as possible. And then throughput is nothing but the number of processes executed in a unit of time. And then turnaround time is nothing but the total execution time. This includes that waiting time also. Then waiting time of a process is nothing but the amount of time that a process is waiting in the ready queue to get the CPU. And then response time is nothing but the amount of time it takes from when a request was submitted until the first response is produced. That is, from the time at which that process is placed or arrived in the ready queue and to the time at which it is getting the first response. This particular duration is called response time. So by analyzing or by calculating these criteria, measures, we can say a particular algorithm is best one or worst one. So in this case, an optimal algorithm should produce CPU utilization of high, maximum. That is maximum CPU utilization and maximum throughput, minimum turnaround time, minimum waiting time, and minimum response time. So if a process, if an algorithm is having maximum utilization, maximum throughput, minimum turnaround time, minimum waiting time, and response time are considered as the best algorithm. So now let us consider a small example here. 4 processes are taken and 4 processes are given along with their burst time and their priority, and their arrival time is also given. That is the time at which these processes are placed in its ready queue. So now we'll consider this example and find the turnaround time and waiting time for different algorithms. That is for first come first serve algorithm, for shortest job first algorithm, for round robin algorithm, for priority scheduling algorithm. And after finding that turnaround time and waiting time, we'll compare their performance. Okay, now we are going to find average waiting time and average turnaround time for these processes for different algorithms. First, I am going to take FCFS, that is first come first serve algorithm. So for first come first serve algorithm, to calculate that waiting time, first we have to draw Gantt chart. From the Gantt chart, we can easily calculate waiting time and turnaround time of each and every process. So the Gantt chart is drawn for different processes, the order in which that the processes are getting the CPU. So the processes are arrived at different times. So process P1, it is arrived at the time of 0th millisecond. So here this is first come first serve algorithm. So the processes are allocated the order in which they are arriving. So P1 can get the CPU first, then P2, then P3 and then P4. So these are all this FCFS is supporting for non-preemptive. So P1 is getting the CPU and it is getting the CPU in the 0th millisecond, and this can be executed for 8 milliseconds. And then in the 8th millisecond, process P2 is getting the CPU and this can be executed for 4 milliseconds. So 8 plus 4, 12. And then next process P3 is getting the CPU and this can be executed for 3 milliseconds. So 12 plus 3, 15. And finally, process P4 is getting the CPU and can be executed for 5 milliseconds. So P4 is getting the CPU and can be executed for 5 milliseconds. So 15 plus 20, 15 plus 5, 20. So now from this Gantt chart, we can easily calculate the waiting time of each and every process. So waiting time of process P1 is at what time that the process is getting the CPU and how much time that the process is waited in the queue. So P1 is arrived at the time of 0th millisecond and immediately CPU is assigned. So its waiting time is 0 millisecond. Then process P2 is getting the CPU in the 8th millisecond, but it is arrived only at the 1st millisecond. So it is getting the CPU. So its waiting time is 8 minus arrival time. So it will become 7 millisecond. Then P3 is getting the CPU in the 12th millisecond. So its waiting time is 12 minus its arrival time. It is arrived only at the time of 2nd millisecond. So 12 minus 2. So this will become 10 millisecond. Then similarly P4, its waiting time is 15 minus its arrival time. It is arrived only at the 3rd millisecond. So 12 millisecond. Now we have to calculate that average waiting time. So average waiting time is nothing but add all these all processes waiting time and divide it by total number of processes. So 0 plus 7 plus 10 plus 12 divided by 4. So this will become 10, 22, 29 divided by 4. So this is equal to 7.25 milliseconds. 7.25 milliseconds. Then after calculating waiting time, we can calculate turnaround time. Turnaround time of a process is nothing but waiting time of the process and its burst time. So we have to add waiting time of the process with the burst time of the process. So turnaround time of process P1 is waiting time of process P1, that is 0, and its total burst time 8. So 8 milliseconds. Then for P2, its waiting time is 7 plus its burst time 4. So it's 11 milliseconds. And for P3, its waiting time is 10 and its burst time is 3. So 13 milliseconds. And for P4, its waiting time is 12 and its burst time is 5. So 17 milliseconds. So average turnaround time is nothing but each and every process their turnaround time is added and it will be divided by 4 because we have considered 4 processes here. So this is 30, 40, 41, 49. 49 divided by 4. So this is equal to 1 to 12.25 milliseconds. 12.25 milliseconds. So this is for first come first serve. The next algorithm is SJF. So we have to calculate waiting time and turnaround time for next algorithm SJF. So SJF for non-preemptive. SJF is supporting for both preemptive and non-preemptive. So here we will consider SJF for non-preemptive. So here again we have to draw Gantt chart. Then from the Gantt chart we can calculate waiting time and turnaround time. So here SJF is nothing but a process with the smallest burst time is getting the CPU. So here all these processes are arrived in different times. So in the 0th millisecond only one process is available in the queue, that is P1. So only one process is there, so there is no option. So whatever may be the the burst time, this process is getting the CPU. So P1 is getting the CPU first. So there is no other process available in the queue because they are arriving at different times. But this is non-preemptive. So once CPU is allocated to this particular process, this process never give up the CPU. So it can continue its execution, and after completing its execution only, CPU can be given to assigning some other process. So this process can continue its execution for 8 milliseconds. Then in the 8th millisecond, that scheduling algorithm SJF can view all the processes available in the ready queue. So 3 processes are already arrived. That last process arrived in the queue is third millisecond. It is P4. So now 3 processes are there. Among the 3 processes, that process P3 is having lowest burst time. So P3 is getting the CPU. So P3 is executed, and P3 its burst time is 3, so 8 plus 3, 11. Then P2 and P4. P1 has completed its execution, P3 has completed. Now P3 and P4, among these two, P2 is having the burst time of 4. So P2 is getting the CPU and can be executed for 4 milliseconds. So 11 plus 4, 15. And finally P4 is getting the CPU and can be executed for 5 milliseconds. So 15 plus 5, 20. So now that Gantt chart is drawn, we have to calculate the average waiting time and turnaround time. So waiting time of process P1. For process P1, it arrived only at the time of 0th millisecond and immediately it got the CPU. So its burst time is, its waiting time is 0. Then P2 is getting the CPU only at the time of 11th millisecond. So its waiting time is 11, but it is arrived at the time of 1st millisecond, minus 1. So 10 milliseconds. Then P3 is arrived, it is getting the CPU in the 8th millisecond, so its waiting time is 8, but it is arrived at the time of 2nd millisecond, so minus 2. So this is 6 milliseconds. And P4 is arrived at the time of 3rd millisecond, but it is getting the CPU at the time of 15th millisecond. So 15 minus 3, so 12 milliseconds. So average waiting time is equal to 0 plus 10 plus 6 plus 12 divided by 4. So this is equal to 28 divided by 4 is equal to 7 milliseconds. Waiting time of average waiting time of SJF for non-preemptive is 7 milliseconds. Now we have to calculate the turnaround time. So turnaround time is nothing but waiting time of each and every process is added with burst time. So waiting time of P1 is 0 and its burst time is 8. So 8 milliseconds. Waiting time of process P2 is 10 milliseconds. Its burst time is 4. So 14 milliseconds. Then waiting time of P3 is 6 milliseconds and its burst time is 3. So it is 9 milliseconds. Then waiting time of P4 is 12 milliseconds and its burst time is 5. So 17 milliseconds. So now we have to find average turnaround time. So average turnaround time is equal to 8 plus 14 plus 9 plus 17 divided by total number of processes, that is 4. So this is equal to 10, 20, 20, 30, 36, 36, 30, 40, 48. So 48 divided by 4. This is equal to 12 milliseconds. So for FCFS, its turnaround time is 12.25, but here it is 12 milliseconds. So 0.25 milliseconds are reduced here. The next we will consider the next algorithm, SJF. Average waiting time for SJF non-preemptive is 7, and turnaround time for FCFS is 12.25. Then average waiting time for FCFS is 7.25. Now we will calculate waiting time for SJF preemptive. SJF preemptive. So again we have to draw the Gantt chart. So as usual, here process P1 is arrived at the time of 0th millisecond. So in the 0th millisecond only one process is there, that is P1. So no other option is there, choice is there. So P1 can get the CPU initially. So in the 0th millisecond P1 can get the CPU. It is preemptive. So preemptive means at any time that a process can be preempted from the CPU can be preempted from the currently executing process. So P1 can be executed until that the next new process is arrived. So here the next new process P1 is entering into the ready queue at the time of first millisecond. So P1 it is already executed for 1 millisecond. So this is executed for 1 millisecond, and its remaining burst time is 7. So it is executed for 1 millisecond and its remaining burst time is 7. So the remaining burst time of currently executing process is compared with the burst time of newly entered process. Newly entered process P2, its burst time is 4. So 4 is compared with the currently executing process, its remaining burst time. So 4 is smaller than 7. So CPU is preempted from the P1, and that will be allocated to P2. So P2 can get the CPU now, and P1 it is executed only for 1 millisecond. So it has to be executed for 7 more milliseconds. So here P1 can be executed until another new process is arriving. So new process P3 arrived at the time of 2nd millisecond, but its burst time is 3. So now P2 is executed for 1 millisecond again, and its remaining burst time is 3. So remaining burst time of P2 is now compared with newly entered process P3's burst time. So both are equal. So P2 never give up that CPU, it can continue its execution. So P2 can continue its execution until the next process is arrived. So next process arrived is at the time of 3rd millisecond. So it can be executed for 2 milliseconds. So next process P4 is arriving at the time of 3rd millisecond. Its burst time is 5, and P2 has already executed for 1 more millisecond. So its remaining burst time is 2. Remaining burst time of P2 is compared with P4, and now P4 its burst time is 5, which is greater than that remaining burst time of P2. So P2 can continue its execution. So P2 is executed for 4 milliseconds. So here P1 is executed for only 1 millisecond, and P2 can continue its execution for more 4 milliseconds. Then this will become 5. Then now 3 processes P1, P3, P4 are there. Among them a process with the smallest burst time is getting the CPU. So P3 its burst time is 3. So this its execution is over. So P3 is getting the CPU next, and this can be executed for 3 milliseconds. So 5 plus 3, 8. And then P4 is getting the CPU and can be executed for 5 milliseconds. So 8 plus 5, 13. And finally P1 with a burst time of 7 can be executed. So it is assigned CPU, and it continued its execution. So it can complete its execution at the time of 20th millisecond. So now we have to calculate average waiting time. So for every process we have to calculate waiting time first. So waiting time for process P1. So here P1 is getting the CPU for 2 times. So we have to take that latest CPU allocation time. So CPU is allocated to the P1 in the 13th millisecond minus arrival time. Its arrival time is 0 minus how much time that the process is already executed by the CPU, because here that the process is getting the CPU more than one time. So latest CPU allocation time is 13 minus arrival time minus how much time that the process is already allocated or executed by the CPU. So this is executed for 1 millisecond. So 1. So this will become 12 millisecond. Similarly, P2, it is getting the CPU at the time of first millisecond. So 1 minus its arrival time is 1. So its waiting time is 0. Then P3 is getting the CPU at the time of 5th millisecond, but it is arrived in the 2nd millisecond. So its waiting time is 3 millisecond. Then P4 is getting the CPU at the time of 8th millisecond. So its waiting time is 8 minus its arrival time. Its arrival time is 3. So 5 millisecond. So average waiting time is equal to 12 plus 0 plus 3 plus 5 divided by 4. So this will become 8. 20 divided by 4 is equal to 5 milliseconds. So now we have to calculate that turnaround time. So turnaround time for process P1, this is nothing but waiting time plus burst time. So P1, its waiting time is 12 milliseconds. So 12 plus its burst time 8. So it is 20 milliseconds. Then for P2, its waiting time is 0 and its burst time is 4. So 4 milliseconds. Then P3, its waiting time is 3 milliseconds and its burst time is 3. So 6 milliseconds. Then P4, its burst time is, that is its waiting time is 5 and its burst time is also 5, so it is 10 milliseconds. So now that average waiting time is 20 plus 4 plus 6 plus 10 divided by 4. So 20, 30, 40. 40 divided by 4 is equal to 10 milliseconds. 10 milliseconds. So now we will go to next algorithm called priority scheduling. So here I'll copy that values for FCFS. For FCFS, its average waiting time is 7.25. Then average turnaround time is 12.25, and for SJF non-preemptive, average waiting time is 7 milliseconds and average turnaround time is 12 milliseconds. And similarly for SJF preemptive, its average waiting time is 5 milliseconds and average turnaround time is 10 milliseconds. Now we will go for priority scheduling. So priority scheduling. So for priority scheduling, let us take a non-preemptive. Non-preemptive. So we have to draw a Gantt chart. So process P1, it is arrived at the 0th millisecond. So only one process is there. So we have to, that is the CPU should be allocated to that particular process. Whatever may be its priority. And here the important thing is, for other algorithms, we should not consider that priority. For priority scheduling only, if priority is given in the problem, we have to take that priority assigned to each and every process. So P1 is getting the CPU in the 0th millisecond, and it is non-preemptive. So this can be executed for 8 milliseconds. Now in the 8th millisecond, after the completion of P1, already all the three processes are arrived. Now we can check, that is that CPU can be assigned to the processes based on their priority. So P2, P3, P4. P2 its priority is 3. P3 its priority is 2 and P4 its priority is 1. So P4 is having the highest priority. So P4 is getting the CPU next. So P4 can be executed for 5 milliseconds. So 8 plus 5, 13 milliseconds. Then P3 and P2, among them P3 is having highest priority, that is 2. So P3 is getting the CPU and can be executed next. So P3 is executed for 3 milliseconds. So 13 plus 3, 16. And finally P2 is getting the CPU and can be executed for 4 milliseconds. So 20 milliseconds. Then after calculating that Gantt chart, now we can calculate that waiting time and turnaround time of each and every process. So waiting time of process P1. P1 immediately it got the CPU, so its waiting time is 0. And P2 is getting the CPU in the 16th millisecond. So 16 minus, its waiting time is 16 minus its arrival time. It is arrived only at the time of 3rd millisecond, so 3. So 13 millisecond. And similarly P3 its waiting time is 13 minus its arrival time. It is arrived only at the time of 2nd millisecond, so 2. So here it is 11 milliseconds. Then P4 is arrived at the time of 3rd millisecond and it is getting the CPU in the 8th millisecond. So 8 minus 3. So this will become 5 milliseconds. So now average waiting time is equal to 0 plus 13 plus 11 plus 5 divided by 4. So this is equal to 20, 24, 29 divided by 4. So that is 7.25 milliseconds. 7.25 milliseconds. So this is for priority, non-preemptive, its average waiting time. The next one we have to calculate turnaround time. Turnaround time for each and every process. For process P1, its turnaround time is waiting time plus its burst time. So 0 plus 8 milliseconds. Then for P2, it is 13 plus 4. So 17 milliseconds. Then P3, its burst time is 3 and its waiting time is 11. So 11 plus 3, 14 milliseconds. And P4, its waiting time is 5 and its burst time is also 5, so 10 milliseconds. So now average waiting turnaround time is 8 plus 17 plus 14 plus 10 divided by 4. So that is equal to 30, 44, then 51. 51 divided by 4. So this is nothing but 111, so 2.330, so this will become 85 milliseconds. 85 or I think 75 milliseconds. So now the turnaround time of average turnaround time of priority scheduling for non-preemptive case, it is 12.75. So now we will calculate waiting time and average waiting time for round robin scheduling. So round robin, here the time quantum given here is 4 milliseconds. So now draw the Gantt chart. So here the thing is, all the processes can be executed only for 4 milliseconds. If its time is exceeding, its burst time is exceeding, means then that process will be moved to the tail of the ready queue and it will be getting the CPU after some time. So here process P1 arrival time is given. So P1 is the only process available in the 0th millisecond. So P1 can be executed for only 4 milliseconds because the time quantum assigned is 4 milliseconds. So it can be executed for 4 milliseconds. So its remaining burst time is 4. Remaining burst time is 4. So now in the 4th millisecond, it will check whether any other process is arrived. So all the 3 processes are arrived at the 4th millisecond. So it will, the CPU will be allocated to next process, P2. So P2 can be executed for 4 milliseconds. So 8. So now P2, its execution is over. Now P3, the next process available in the queue is P3. So P3 is, its burst time is 3. So P3 can be executed for 3 milliseconds and once its execution is completed, then CPU can be allocated to next process in the queue. So it can be executed for 11 milliseconds. Now its execution is also completed. The last one P4 can get the CPU for only 4 milliseconds. So 11 plus 4, 15. Now its execution is not completed. Still it need 1 more millisecond. So this will get the chance after that P1's execution is over. So P1, its remaining burst time is 4. So next P1 can get the CPU and be executed for 4 milliseconds and finally P4 will get the CPU and can be executed for 1 milliseconds. So this is the Gantt chart for round robin algorithm with a time quantum of 4 milliseconds. Now we have to calculate turnaround time, waiting time. So waiting time of P1 is getting the CPU for 2 times. So the latest time is 15 minus its arrival time 0 minus how much time already that particular process is executed by the CPU. So it is executed for 4 milliseconds. So 4. So its waiting time is 11 milliseconds. Then P2, it is getting the CPU in the 4th millisecond. Its arrival time is 1. So its waiting time is 3. And third one P3. P3 it is executed only once. So P3 is getting the CPU at the 8th millisecond and its arrival time is 2. So it will become 6 milliseconds. And finally P4 is getting the CPU more than 1 time. So its latest allocation time is 19 minus how much time already, how much period that the process is already executed by the CPU. This is 4 minus its arrival time. So that is 3. So 12 milliseconds. So average waiting time is equal to 11 plus 3 plus 6 plus 12 divided by 4. So this will become 29, 30, 32. 32 divided by 4, it is equal to 8 milliseconds. Then similarly, we have to calculate turnaround time. So turnaround time of P1 is nothing but its waiting time plus burst time. So waiting time is 11, its burst time is 8. So P1, its turnaround time is 19 milliseconds. Then for P2, its waiting time is 3, its burst time is 4. So 7 milliseconds. Then P3, its waiting time is 6, its burst time is 3. So 6 plus 3, 9 milliseconds. Then P4, its waiting time is 12, its burst time is 5. So 12 plus 5, 17 milliseconds. So average turnaround time is equal to 19 plus 7 plus 17 plus 9 divided by 4. So this is equal to 20, 40, 20, then 30, 38, 38 plus 40, 54, 54, or sorry, 52 divided by 4. So this is equal to 13 milliseconds. 13 milliseconds. So now we have calculated average waiting time and turnaround time for all the algorithms. We can go for comparison now. So here already the average waiting time for FCFS, SJF is given. So among them, for FCFS, its turnaround time is average turnaround time is 12.25. For SJF non-preemptive, it is 12. For SJF preemptive, it is 10. So 10 is the minimum. Then here for priority, its turnaround time, average turnaround time is 12.75. So 10 is minimum here. And for round robin, its average turnaround time is 10 milliseconds. So that round robin and SJF preemptive is producing better results. So this is a case for this particular set of processes. So every algorithm can produce better results for different set of processes, nature of the processes. So its performance may vary. So according to this particular cases, this particular example, that SJF preemptive and round robin is producing better results. Algorithms are optimal for this particular example. So nowadays operating system, that is different scheduling algorithms are used by different operating systems, and that the CPU scheduling is also one of the important factor that decides the performance of the computer. So that the developer has to select CPU scheduling algorithm for their operating system. So with this I will conclude this session. I hope this information will be useful for the students who are studying the operating systems paper and students who are getting ready for placement. Thank you.